Now let's discuss the wide variety of moons that we find in our solar system. This image is just a small sample of these moons that we see out there, comparing them in sizes to scale. And we see just this huge variety. Some that very clearly have some kind of atmosphere, some thick atmosphere around them, to others that are just very dead in a geological sense. So what we're going to build up here is the language that we'll use to describe the various properties of these moons. And one thing that I just have to point out, the slide used to say that Jupiter was the moon king, and now Saturn has stolen that title. Here are the two moons of Mars, Phobos and Deimos, about 22 and 12.6 kilometers in diameter. And what we'll notice about the moons in our solar system, about 200 of them in total, is that we found dozens of these tiny worlds. Some of them are just basically rock and ice. Others are big, others are small. Some will have potentially liquid water underneath the surfaces. So there's a wide variety in what we'll see in the moons of the solar system. Here's the moon of Ganymede, where we have this material that's differentiated. We'd say Ganymede does have an iron core surrounded by rocky mantle. Processes are driving enough such that underneath the surface there is literally this ocean, this icy mantle. Above the mantle, this ocean, kind of a salty mixture. Anything on the surface, just a nice, icy, crusty surface. This isn't indicative of all the moons, just some of what we see out there. So emphasis we'll have is that the moons that we talk about, they're made of rocks, ice, or both. And some were formed by processes of accretion, remember the sister theory. And others, this differentiation. This is an example of differentiation. The denser materials fall down towards the core, while the lighter materials, the less dense, are pushed upwards. The first category of moons we'll talk about are the regular moons, and these fall into that category of being created by accretion or differentiation from materials that were present around the planet. And what we've seen out there is that about a third of the moons that we have found in the solar system are regular. Now, why did we name the smaller group the regulars? It's just a process of discovery. Anytime there's a question of why do we use a weird naming convention, it comes from a scientific historical perspective of we found X first, that became the regular, and found Y later, that made the picture way more complex. And that language just sticks with us. So, recap. The regular moons, they're about a third of what we find in the solar system. The animation here are showing the Galilean moons, starting from the inside, Io, Europa, Ganymede, and Callisto going outwards. These are the Galilean moons. And as they go around, their orbits are mostly tidally locked with the planets. And they orbit in the same equatorial plane of the planets. They don't have any chaotic orbits that cause them to shift up and down and have all sorts of weird tumble effects in them. Some of the regular moons can have some strange orbital properties. Look at Phobos and Deimos as they go around on Mars, and you'll notice how rapidly Phobos is swirling around the Martian planets. Well, it turns out that Phobos moves so quickly that it will rise and set twice in a given Martian day. Hyperion, which is a moon of Saturn, can be seen going around in this kind of crazy, it looks like it's a growing spiral, but what will actually happen with its orbits is that it will spiral outwards, spiral in, spiral out again. And so it's just going to have this kind of just growing width of a space it can occupy as it's floating around Saturn. Hyperion does these weird, tumbles around the planet as it orbits. I mean, what I mean by that is that the planet, the moon itself, is twisting and rotating, not in its orbit, but on its rotational axis. Now, outside the regular moons, there are the irregular moons, and these tend to be objects that were gravitationally captured by the planet. They'll look like floating debris of rock that's just floating around in the cosmos. This is Phoebe, Saturn's largest irregular satellite. One of the primary characteristics that tells us if it's an irregular moon is its retrograde or backwards orbit. And that comes back to this concept of being a captured object. Largest out there will be a moon of Neptune called Triton. And these things can range from a few to literally hundreds of kilometers in diameter. Now, in trying to give the rest of our conversation some focus, we're going to talk about major moons and their defining characteristics. This is a simulated view of what it looks like on the surface of Europa, and you see Jupiter and the Sun rising on your horizon there. So, from here on up, we'll still have discussions of categories of regular versus irregular moons, but the next thing that we're going to use is talk about their geological activity. And here's how we'll break them up. Sometimes we'll see surface markings that indicate craters, there'll be dark or bright spots, and these will be signs of what kind of geological activity is happening on these moons. So a question that is fair to ask is, hey, are some of these moons will have atmospheres, have magma, why are they not planets? And what is the definition of a planet? That definition will come to you in the next section, I promise. But I want to mention it now to get you thinking about it. So, switching back to the geological activity, we're going to categorize our moons with these labels here. The ones that are geologically active now, like you see in Io here, where there's literally magma flowing on the surface. Or these dark spots is potentially sulfur snow. Then we switch to the moons that are possibly active. We can't definitively say they have geological activity, but the signs on the surfaces imply there probably is. And we'll find ones that were definitely active in their past lives, but have since died off. Most likely, best explanation, they cooled off. They just don't have enough geological or tectonic activity from the internal heat to drive anymore, or geological activity. And then the last category will be just dead rocks. Rocks that were never geologically active. Continuing our discussion of Io, Io is one of the geologically active moons in our systems. Turns out one of the most active objects in the solar system. And what drives it is not some big internal source of heat from, say, like on Earth, radioactive materials decaying, heating the interior of this planet. Io's comes from tidal stretching. Io is being constantly flexed and compressed from just orbiting around Jupiter and creating extreme tidal forces on it. So let me switch to my little paperclip example to give you an idea of what I mean. So I'm going to use my little paperclip here to demonstrate what I mean by tidal stretching. As Io goes around Jupiter, what's going to happen is that it's going to flex and stretch. So let me break this, well, not break it yet. Let's get this thing unfolded. So here's my paperclip, and tidal forces. Remember, just like how the moon creates tides on Earth, you can have tidal forces on Jupiter on its moon Io. And so as it orbits around, it will stretch. Oh, did that too quickly. Let me try another paperclip. Always come prepared. So let's try this again. I'll have a. Can you see that one? All right. It was a little bit closer. So here's my paperclip, and we're just going to tidally stretch it out. Go ahead and do. So as it orbits around, it's going to flex a little bit, then stretch, then flex, then stretch. And this is constantly happening on Io. Now this will come up relevant later when we talk about rings. What happens when I flex too much? If I flex the paperclip too many times or too rapidly, you can start to feel it heat up. It'll start to warm. It'll get weaker and weaker. Come on. Go ahead. And snap. Think about where rings come from. All right. So this is what I mean by tidal stretching. This object, this material being stretch, compress, flexing constantly over and over again. Because of the tidal stretching of Io due to its proximity to Jupiter, it gets to be the most volcanically active object in the entire solar system. Here are pictures of one example of activity happening, going away, and coming back, constantly erupting, spewing lots of material. So Io is the most geologically active thing in the solar system. Venus may have claims to being the planet with the most volcanoes, but in terms of what is the geologically active thing, it's Io. Continuing on the topic of the geologically active ones, here is Enceladus, a moon of Saturn, and you can very clearly see smooth surfaces with kind of veins going across it. An image that Cassini captured shows these bright spots of material being ejected outwards. And what we understand now is that this is an example of what's called cryovolcanism. There is volcanic activity happening on Enceladus, but instead of molten rock, it's molten water? Yes, literally. Remember, on these surfaces, these are icy, crusty features, but underneath that, you can have molten ice, which we just call water. And it's the same principles of magma and volcanoes here on Earth. It's just instead of having a melted rock be the volcanic material, it's water. And that thermal energy can be driven up through the cracks, through the veins, and constantly eject material out into the solar system. In fact, the material that's escaping from Enceladus is actually fueling one of the faint rings on Saturn. It's constantly spewing material out there to keep the Saturn's ring stable. The last geologically active moon we'll talk about is Triton, which is Neptune's largest moon. And you can very clearly see smooth surfaces, the vein-like features, and then crusty surfaces. So this is another irregular moon. It's in retrograde orbit, and it'll have cryovolcanic activity of nitrogen. And this thing's massive enough that it does retain a thin atmosphere around it. Switching to the possibly active ones, we've got our first one, Europa, which is by far my favorite moon. And what we mean by possibly active is that we look at pictures of the surface. Here's an image from Galileo spacecraft, about 70 kilometers wide here. And you see these ice slabs. And it looks like they might be able to slide around on top of each other. That's kind of the pictures you're seeing here. Are these slabs of ice actually sliding around? Can't say definitively, and this is why we mean by the possibly actives. Another thing about Europa is that, yes, its interior can be heated by tidal frictions, but it's not enough for volcanic activity. But it could allow for underneath the surface of Europa to be liquid, meaning that there's potentially underground lakes underneath the crusty surfaces of Europa. Titan's a great moon to discuss because it really drives at this heart of what's the difference between a moon, a planet, a dwarf planet. Because look at this thing. Titan is slightly larger than Mercury and has a thick atmosphere. It's 30% denser than ours on Earth. This moon itself is composed of water, ice, and rocky materials, and it has its own cloud systems, its own storms that happen on there. One of the primary factors is this idea of this photodissociation, which is UV photons coming in, hitting the upper layers of this atmosphere, and breaking apart ammonia and methane in the atmosphere. This should remind you of ozone on Earth. Oxygen molecules in our troposphere are absorbing UV rays and being photodissociated. Even crazier parts about Titan is that this means that there's probably rain of methane or ethane there. There is this literal downpour of these gases into liquids on this moon. And because of its potentially geological activity, it could be fueling a cycle of driving material up there. We don't have a good idea if this is happening, but we're very suspicious that it does. So suspicious that we've even sent landers there. This is a Huygens lander. These are 360-degree perspective as the lander was plummeting down and landing onto Titan. And we found what we keep talking about: icy rocks and a soil that's very rich with organic compounds. Organic's just a nice way of saying lots of carbon there. So we think that there are literal lakes of hydrocarbon materials on the moon Titan. The next category of moons will be the formally active ones, and Ganymede's a perfect example of this. You can very clearly see impact craters, but they're smoothish. So what this is a sign of is that this was an impact crater that did hit the surface of this moon, and in a previous part of its life, it was geologically active enough that it could fill these impact craters, or tectonic activity could have been happening to smooth out the surfaces of the moon. So how does those impacts get filled? Well, it's a process we call the filling this impact scar. So here's the scar. Here's the impact coming in, and like we've discussed before, and it leaves this result. However, on these formally active moons, what could happen is that liquid material would fill it up, settle down, and ice over again. So this smooth fluid would ooze in here into the crater, solidify back into the icy, crusty surface, and then have that crater filled. Now, as time goes on, you'll eventually lose enough thermal energy in these moons that they just can't provide any liquid to fill that up anymore. So these formally active moons are ones that were very hot beginning of its life and just cooled off over time. One more of the formally active ones I want to talk about is Mimas, moon of Saturn. And honestly, the only reason I wanted to show you this, guys, is because I call it the Death Star moon. I know, big nerd, but I gotta get these things in there when I can. So of points that matter, these moons do show that they have formally active. You've got regions of dark versus bright, which is distinguishing, hey, could there have been former activity there? All right. And here's a list of moons that kind of fall into these categories of they used to be active objects. Key emphasis here, what provided this was the internal heat from the formation of these moons, and that has since dissipated away. And these moons fall in a region where that tidal heating just isn't enough to drive geological activity. The final category of moons are the geologically dead ones, and I bring back Callisto as my prime example. This thing shows no signs of geological activity ever. And you'll have regions of heavily dark cratered regions versus the bright ones. The bright ones are probably ice that has been exposed from other impacts. Impact came in and just liberated enough of the rocks on the surface, showing the ice underneath, very thin layer. So the last thing we'll talk about these moons is there potential for life on them? We've literally seen moons that are as big as planets and have their own atmospheres and chemistry and rains. So one example, this is a picture potentially on Europa's surface, where on the surface layers it's a thick ice, but you could have veins there, cracks forming, where we see potential plumes of liquid water being jettisoned out there. And from that, we've seen on the surface complex molecules that are being broken down from radiation being absorbed in the surface layers. But where'd those complex molecules come from? They came from the oceans. Remember, this is that cryovolcanism. This is a sea, an entire ocean of material, or life potentially. And it ekes out there through the cryovolcanoes, gets thrown up, and crashes back down to the surface of this moon, where we can see signs of these molecules. So there are several candidates for potential life on them. And my vote is we send a spacecraft to Europa, and we drill down that crusty surface and see what kind of fishes are swimming around in that ocean.